Alright, so I'm Rodney Horn, wateropseducation.com, and we're going to be talking a little bit about iron and manganese removal today. I am in the process of preparing this course to be presented online for continuing education purposes in North Carolina, and probably going to expand from there, but we'll just have to see how long that's going to take here. I'd love for you guys to give me some feedback on this. I'm going to be putting it on YouTube. I'm probably going to offer a lot of this information a little more openly here. The goal of Water Ops Education is to help operators, not keep a lot of information in reserve until you pay for a continuing education course or whatnot. But that will support the operation, so let's go ahead and get into this iron and manganese control and drinking water treatment and see what we got here. Alright, this is copyright 2016 Water Ops Education and Rodney Horn. Alright, there's a little welcome. That's going to be more for folks on the continuing education side. And if you got any questions or comments, you can just use that email address right there. Questions@wateropseducation.com. And for the YouTube video, I know you guys have no idea probably what I'm talking about, but there'll be a PowerPoint slideshow going along with this. So anyway, this is really, for online purposes, this is really just to give you a feel of maybe what the presentations are going to be like. But once you're actually taking a course online, you'll have me talking up in the corner, and then you'll have your main slideshow that you'll actually be reading, and you can go back and forth. You can shut me off or whatever you want to do, and of course there'll be checkpoints along the way. So let's see. All right. The elements, iron and manganese, also from the periodic table, you'll see Fe and Mn. They're often found together in drinking water sources. This includes both groundwater and surface waters, such as rivers, lakes, and man-made reservoirs, of course. All right, iron is the fourth most abundant element at 5.6% of the Earth's crust, and manganese actually represents less than 0.1%. So for 0.1%, manganese sure can cause a lot of trouble. Although they do not pose a threat to the public health, iron and manganese can be a nuisance in water systems for several reasons. They stain fixtures and laundry, as well as imparting color to the water, and this can lead consumers to feel their tap water is not safe to drink. All right, the presence of these two elements encourages the growth of certain types of bacteria, and if anybody's ever seen iron bacteria coming out of a well, you know what I'm talking about. Bacteria use reactions between metals and dissolved oxygen for energy. As the bacteria grow, they form slime molds that can coat the insides of plumbing. Iron and manganese can also be oxidized in the distribution system. This results in the formation of manganese dioxide and rust particles as well. Manganese dioxide is a particulate also. Oxidants can include disinfectants used in the distribution system, as well as dissolved oxygen that may be present in the water. Discolored water is a major source of customer complaints in the water industry. Well, I think anyone in the water industry on the municipal side knows what it's like to get those phone calls. So don't look forward to them, especially at 5 o'clock. Settled particles and slime molds may flow to the consumer's tap when there's a disruptive event, such as a line break or a high flow condition in the system. A guide for troubleshooting red water is actually found at the end of this presentation, and basically that comes from the Sacramento manual, so I'll give you a reference for that here at the end, so you can just pull it up. I think pretty much right now everyone who's going to be using this course is familiar with the Sacramento manuals, and I may be wrong, but I think Texas and New York are the only folks who don't use the Sacramento manuals. I may be wrong about that. If you know, please, if you're in another state and you guys don't use the Sacramento manuals, let me know, because I'm really curious about that. All right, the recommended limits for iron and manganese. Okay, it only takes a small amount of iron and manganese to create plumbing problems, and the EPA recommendations for recommended contaminant levels are 0.3 milligrams per liter for iron and 0.05 milligrams per liter for manganese. So you can see the manganese can cause a problem at quite low amounts. EPA considers these secondary limits. Secondary limits are non-mandatory standards that are recommended by the EPA in order to reduce color, taste, and odors that may be objectionable to your consumers. And there's a web address here for more information on secondary limits from the EPA website. A lot of good stuff on the EPA website, by the way. All right, we're going to go down to iron problems here. And when you're actually taking the course, there's going to be some photos of iron problems, discoloration and staining and whatnot. Or if I've actually revamped this thing by the time you watch it, and I'm actually showing on, well, yeah, I could do that. I could just separate out these tracks anyway and put this as narration with the slideshow online. But anyway, so we'll see. But I'm definitely not reshooting this whole thing because I rearrange how I do it. Because at this point right now, this is just for information purposes. Okay, we're going to have some manganese images on there also. Manganese, and some manganese and iron in a dishwasher. And right now, let's talk about more on dissolved iron and manganese. In low oxygen environments, iron and manganese exist in their ionic forms. These are Fe2+ and Mn2+. That's ferrous and manganese ions. These ions can also be written as iron with the Roman numeral 2 in parentheses, and manganese, Mn, with the Roman numeral 2. And let's see, these are the conditions you're going to find iron and manganese in the hypolimnion of lakes and reservoirs. And the hypolimnion is just the low dissolved oxygen levels down towards the bottom. These iron and manganese ions are going to stay in solution in that case. They're going to keep that +2 charge, and they're just going to be in there. They're not going to be in a particulate form. They're not going to sink or settle out. Now, when they're exposed to an oxidizer, such as oxygen, let's see what else, chlorine, several others, they're going to form insoluble compounds, such as oxides of iron and manganese dioxide, and these solids are then going to settle out in the distribution system. Also, the reason for groundwater high in dissolved oxygen would typically contain rust, which is also, you see this in the horizontal wells that pull from beneath rivers a lot. All right. Seasonal turnover in lakes and reservoirs often result in periods of high iron and manganese problems. Warmer water on the reservoir surface is going to cool off in the wintertime. It's going to mix with the deeper water layers. The cooler, lower layers contain less dissolved oxygen. So these the excess ionic forms we just talked about are going to be present, and they're going to mix in with that high DO water, maybe form some particulates, but you're also going to have a better chance of pulling them into the water treatment plants. Usually, of course, usually your intake levels are set at certain heights, and you don't want to pull in a lot of the particulate matter. All right, and we're going to have a lake stratification of iron and manganese chart here. And that's going to show you the epilimnion, the metalimnion, and the hypolimnion, and there's a few notes on the temperatures and whatnot. So maybe I'll just pull that out and put that in as an individual slide, but we'll see. All right, once in the plant, these iron and manganese ions can cause the same problems as you have in your distribution system. They can be oxidized by chlorine and make their way into the distribution system in particulate form. If there's enough of an excess concentration, ionic forms will continue into the system. And of course, then you can have further problems there with oxidation. That's where a lot of your groundwater complaints are going to come from. You'll have your ionic forms, and they'll form basically rust, iron oxides, and manganese dioxides. And of course, you have corrosion going on inside the piping too, which is why a corrosion inhibitor is so important if you have any kind of steel pipes or whatnot. All right, it's worth monitoring water temperature and dissolved oxygen at intakes that can be adjusted at different depths. The intake levels can be controlled to be certain water is being pulled from high DO layers with low concentrations of dissolved iron and manganese. All right, mineral sources of iron, they're going to include ferric oxides, Fe2O3, ferric hydroxides, which is FeOH3, OH being in parentheses with a 3, so 3 hydroxide ions attached there. This is the mineral that gives rocks and soils their color. And actually, I've got some iron ore around here somewhere. Maybe I'll put a photo of it. All right, sedimentary sources include sulfides, pyrite and marcasite. Pyrite's that fool's gold. Both of these have the formula FeS2. However, they have different crystal structures, which is just kind of a little interesting tidbit that probably isn't going to make much difference in your water treatment life. But anyway, all right, you have carbonates like FeCO3, ferric carbonate, or ferrous carbonate, ferric, no, that's ferric. Mixed oxides like magnetite, Fe3O4. All right, ferrous oxides and sulfides are usually the source of dissolved iron in groundwater. Weathering of iron silicates can produce dissolved iron in surface waters. This is a very slow process. Iron is relatively soluble in low oxygen waters, so that Fe2 or Fe3, they're going to go into solution really easy. Low alkalinity groundwaters may actually have up to 10 parts per million of iron, so it's pretty common to have high iron there in your low alkalinity areas. All right, let's talk a little more about bacteria. They're known to grow and proliferate in waters containing as low as 0.1 milligrams per liter of iron. However, at least 0.3 parts per million of dissolved oxygen is needed to carry out the oxidation. Iron bacteria are also present in the soil. Well contamination by iron bacteria is a major concern. Once the bacteria are established in a well, they're difficult to remove. This is why it's important to blow your wells off every so often, because if you do have iron bacteria down in there, you want to get everything flushed out. You much better losing some water out the back end of your well house and your blow off line than having that get on down into your customers' taps and then having to flush out in the distribution system more, because I'm sure you guys know the more you flush in the distribution system, you get your flow rates a little too high. Now you've got even bigger problems. So it's just better just not to let it get in there to begin with, although you still need to flush. And flushing comes up a little more with COC, THM removal these days, but it's a good idea to try to keep your system flushed out. All right, a metallic taste can be detected at iron levels of 0.1 to 0.2 parts per million, actually. And they can create, taste and odor, just taste and odor problems in general at 0.1 to 0.2 part per million. The bacteria you're looking at here are something called Crinothrix and Gallionella. So those are common species of iron bacteria. And I got a little photo of some iron bacteria here that I pulled off the web. I got some iron bacteria built up in a pipe also. And bacteria can be removed by wells also from shock chlorination. So, back up some bleach in there and let it sit. Need to get a procedure for that, see what most folks are doing. Off the top of my head right now, I'm really not sure. Iron bacteria can create taste and odor problems. Surfactants, acids, and alkalis. I think I already said that. Sometimes I get a little repetitive here in some places. I apologize, guys. Surfactants, acids, and alkalis can be used in addition to mechanical scrubbing of the well casing. So scrubbing is an option there. How you scrub the well casing, I'm going to have to look a little closer into, because I've never done that before. Other chemical methods are followed up with chlorination or scrubbing. Chlorination. Maybe I've got that wrong anyway. Why did I say that? Because okay, I see what I was saying there. Okay, you may have like an alkali or an acid, and you may follow that up with shock chlorination, which, the regulations, you have regulations there as far as chlorination goes, which, now that I'm in here, I realize I have left out, so I'll try to look those up for you because I just don't remember off the top of my head right now. All right, our next point here, we're going to get started talking about some treatment options we have for iron and manganese removal, and these are some things that probably aren't really talked about in most certification courses. So we're going to look at that. We're going to look at a little bit of chemistry, but don't worry, it's nothing really outrageous, just some basic knowledge. I may have a little chemical tutorial here at the end just to help some folks out, and I'm probably going to append a little bit of math to this when it's a course. Once again, nothing that's going to be a big pain in the butt. We're just going to look at some basic equations and things that we might find useful, alkalinity usage and that kind of thing. Things that could become practical that we might need to calculate. So, all right, so let's move right along. And cut.